SwayamPrabha. Digital India. Educated India.
Let us start this lecture with a thought process from great Saint Swami Vivekananda, who says, "Truth does not pay homage to any society, ancient or modern. Society has to pay homage to truth or die." This is a very important statement which we need to bother about, as our society is about to die not following the truth in true sense. Let us recall what we learnt in the last lecture. In the last lecture, we initiated the discussion on solid propellant rocket engine. To start with, we looked at why solid propellant rocket engine is sought after even today, although it was started long time back. And what are the applications? We found that it can be applied in several places, starting with the spacecraft, missile and spin rocket engine, vernier rocket engines, that means for the altitude control, and for even like in emergency you can use as a gas generator, and several of them. And as I mentioned, that it will be depending on the imagination of the designer and the user to use the solid propellant rocket engine in various places. And still it is developing and it will be developed further. And then we also compared that where a solid propellant rocket engine can be used and where the liquid propellant rocket engine can be used. We compared both qualitatively and quantitatively, and later on we moved to look at a various components of a generic solid propellant rocket engines. We have seen that it is having a combustion chamber or the casing, solid propellant grain, and it will be having also the liner or the insulator or the inhibitor, whatever you call. There is a layer between the casing and the solid propellant, and of course, the nozzle plays a very important role, and beside this igniter, and sometimes the nozzle closer or a diaphragm is being used for the initiation of the combustion quickly, particularly for a larger rocket engine. And we have looked at two kind of propellant, one is side burning propellant engine and also the end burning propellant engine. Generally the diaphragm is used particularly for the end burning grain or for the larger side burning grain solid propellant rocket engine. Today we will be discussing about the processes involved during the solid propellant rocket engine. If you recall how does the combustion take place, particularly in the gaseous phase, what you might have learned, it is quite easy. That means the fuel and oxidizer will be mixed, or they may be mixed beforehand, that what we call premix combustion, and if the fuel and oxidizer are mixed at the interface of the flame itself, we call it as diffusion flame combustion. But in this case there are several other processes which are occurring. There will be the solid will be converted into the liquid, it can be converted into gas, and then there will be also the transport of this liquid and its vaporization, and it may undergo gasifications, and there will be various kinds of things can happen. So, it is quite complex in nature. Let us look at a general overall view, so that you can get a feel for about it. Let us say this is your solid propellant which I have seen so portion. Of course, this portion also will be solid propellants, and this is the burning surface area what one can see. This is your burning surface, and let us assume that already it is ignited and there is a flame which is occurring in this region. This is your flame which is standing for certain distance. If I say this is a overall exothermic gas phase reaction is taking place and which is located at certain distance, and this we can call it as a standoff distance. That means the distance between the flame and the burning surface of the propellant, we call it standoff distance. And once this flame is established, what will happen, that certain amount of heat will be transferred directly by radiation. If it is radiate, and then it can be re-radiated back from the propellant surface, and there will be also a lot of gases like carbon dioxide, water, some other things which will be absorbing this radiation. And this, beside this, when this also there will be convection which I have not shown, and there will be also the conduction, because this temperature will be very high, this will maybe flame temperature very high, the heat may be transferred toward that. And when the heat will be received at the surface of the propellant at this surface, then what will happen, that it will be also getting conducted towards this heat. That means, this will be heat conducted towards that, and there might be also the pyrolysis of the solid propellants, and because that and also the solid propellant can be gasified, we call it is gasification. Pyrolysis is one in which the thermal degradation of the solid propellant will be occurring in the absence of the oxidizer in theoretically, whereas the gasification will be occurring when the oxygen and fuel ratio is quite low as compared to the stoichiometry. So, therefore, it can be converted directly into the gas, and during pyrolysis maybe there is a liquid layer which will be occurring, this is known as melt layer, and this is a solid propellant, and this portion will be the gas phase reaction will be. And the heat, as I told earlier, the external heat flux due to the convection, there might be a fluid which will be moving, hot fluid on this surface, so that there will be heat flux due to the convective heat transfer. And when it is going radiation can also get into the propellant, the in-depth radiation absorption which will be taking place here. And there might be also pyrolysis which will be occurring in the inside this, and the thermal decomposition it may be coming out. And beside this, there will be some reaction which will be taking place in this. This is known as condensed phase reactions or the surface reaction. This will be occurring in the surface itself. And beside this, there will be phase transition. As I told, the solid can be undergoing changes from its to the either the liquid or the gas or both of them. So, therefore, it will be undergoing the phase change during this surface in this layer which will be taking place, and this is the regression layer, right. So, beside this, there will be a diffusion of the oxidizer and the fuel from this side from the burning surface towards the flame, and there might be some product which will be coming from this gas phase, it will be diffusing towards the solid surface, and oxygen also there will be convection. As a result, it is a quite complex process, and keep in mind that the flow is turbulent in nature. So, therefore, it is very difficult to model this complex process, and some of the processes which are there still not being understood, forget about modeling it. So, it is a quite complex, however, we will be using simple analysis to find out the regression rate of the thing. Now, question arises why we need to know the regression rate and what do we mean by regression rate or the burning rate. So, regression rate is basically can be defined as the burning surface front will be moving perpendicular to the direction of this surface per unit time, right, then we call it as a regression rate or the burning rate. The regression rate, if I take a solid propellant here, let us say, and this is having a surface, this is having a surface here. So, in the beginning it was here, after that it is receding, and as this surface is moving towards this direction, if I say this is x, regression surface, this is your regression surface or the burning surface, whatever you call, you can say also burning surface. And when this burning surface will be getting consumed due to the combustion, it will be moving towards this unburnt or the virgin propellant. This is your virgin propellant, right, and that front will be moving with certain velocity, and that is basically rate of change of the length per unit time, we call it as a regression rate. And why it is important? Because we need to determine the thrust. For that we have seen this equation, that is thrust is equal to m dot p v e plus p e minus p a e. If I say it is a fully expanded, so or we can say that the maximum thrust I can get, the v is the velocity and this is the mass flow rate of the propellant which is passing through the nozzle. But however, this will be equal to the propellant mass be getting consumed, and if I say it is operated under the steady state, that mass flow rate of the propellant or is equal to the mass flow rate of the gas passing through the nozzle, then we which is equal to rho p, that is the density of the propellant, A b is the burning surface area, R dot is the regression rate. So, therefore, if I know this R dot, and of course, the density of propellant will be known for a particular composition, and A b if I know what is the surface area. So, I can find out propellant, and then if I know the V, I can get the thrust, or other way around, if I want to have a thrust, then I will have to have this mass propellant, and then you can calculate from the design case, and of course, the V e will be depend on the area ratio which will be used for in a nozzle, right. And this V we have seen already, it will be dependent on the chamber pressure, it will be dependent on extent of area ratio of the nozzle. So, based on that we can really use this and find out. So, therefore, it is very important to determine and the regression rate. Of course, the process involved during the combustion of the solid propellant is quite complex, and we may not in a position to model this, but however, we will be using experimental data, and also we will be using the some very simple analysis to calculate the regression rate. Whatever we have discussed till now is basically general processes during a generic solid propellant combustion, but however, it may differ from the in case of solid propellant rocket engine. Let us look at the propellant burning mechanism and flame structure for a double base propellant. So, let us look at typical flame photograph of a nitrocellulose nitroglycerin double base propellant. So, if you look at this is your propellant strand, and which is having a flame. If you can look at, this is your flame, luminous flame. This you can say as a standoff distance kind of thing, as I defined earlier. That means the flame is standoff something x dash, and in case B, if you look at this distance, this is your flame, and this distance has been reduced, and it has been reduced in this case, case 3 further. You can see that very easily by observing these 3 photographs. Question arises, under what condition is happening, and even if it is happening, what will happen to the burn rate? That means, if I consider the case A, whether the burn rate will be higher or lower as compared to the case C. So, just to define this further, let me look at another diagram which is very well, it is being illustrated, that is the luminous flame. This is the final product, and this is known as dark zone, or you can call it as a basically lifted, flame is lifted, it is not attaching to that, and this zone and this is of course the propellant stand, and we can call this as a standoff distance also. This region we can call it as a standoff distance. This is standoff distance. So, let us look at the data for all these 3 cases, case A, case B and case C. You can see, and case A, if you look at in figure A, that is corresponding to the 1 megapascal is basically chamber pressure. This is basically PC, chamber pressure is 10 atmosphere pressure, and case B is 20 atmosphere pressure, and case 3 is 30 atmosphere pressure. The regression rate is increasing from 2.2 millimeter per second to 4 millimeter per second. You can see that the regression rate is quite low as compared to the burning velocity of a even like under atmospheric condition, or a simple mixture like methane air. As compared to that, it is very low, although it is at a little higher pressure, which is expected to have a low regression rate, and so also the low burning velocity. And now question arises, why it is so? The obvious answer would be that if the flame is very near to the burning surface, then naturally more heat will be transferred such that the regression will be faster. That is the simple logic one can think about, and one can give. So, let us look at the double base propellant combustion. If you consider that this is basically a solid propellant, which I have shown this portion, and this will be containing this nitroglycerin C3H5 NO3, and this will be containing nitrocellulose 66H XO 5 minus X and X NO3, but and this is basically a polymer, and plus there will be additives which will be there. Now, you can see that the temperature profile during a typical combustion of double base propellant, what is happening, this is your unburnt temperature of the propellant, virgin propellant, and then it goes on increasing, maybe it will be increasing to level where there will be some kind of no reaction will be taking place, or this there is an increase in that, and after that it will be having surface temperature, then it also increases to TD, and then again it will remaining constant for certain zone, and then it will be having flame zone. If you look at this combustion process, looking at this temperature profile, it can be divided into basically 5 zones, and this zone, this is zone, you can say that there is a conduction which is taking place, I can say this portion. This is your heat conduction zone, there will be and this zone is known as foam zone, this portion, this zone is known as foam zone, and this zone is known as fizz zone, and this is known as dark zone, and this portion and this is portion is flame zone. Flame will be occurring here, as I told, this will be the flame which will be occurring, and keep in mind this is being little exaggerated to make this zone very clear. Otherwise, the zones will be very small. It may be if you look at the fizz and foam zone will be order of something micron meter, and the dark zone may be in order of millimeter, and the flame zone will be again will be order of millimeters or even less than that. So, let us look at various heat conduction zone. As I told that during in this zone no chemical reaction occurs. As a result, there will not be any heat will be released. However, the heat will be conducted towards the unburnt temperature, the virgin propellants, these are all virgin propellants through, and as a result the temperature will increase from basically Tu to Ts, the surface temperature, and the solid phase reactions zone, which is we call it as a foam zone, where the propellant decomposition will be occurring. That means, these things will be getting into, if I consider this as a basically R, if I consider R and ONO2, sorry, this is R, NO2, this is basically nothing but NO3 what I have written here. It will be converted in this zone to NO2 and RCHO. This is corresponding to this zone. So, in this zone propellant decomposition will be occurring at around something 500 Kelvin, endothermic chemical reaction will be taking place overall, NO and NO2 and aldehydes, acetaldehydes are formed, and the thickness of this zone is something 10 to 100 micron meter. So, this zone which will the foam zone will be something around 10 to 100 micron meter. And this is a very important zone because it is being decomposed, and then this will be released, and then this is known as a fizz zone because some of the bubbles which will be formed here, and that will be ejected out, and it will be creating some fizz, because foam means there will be some bubble, there will be melted out also sometimes melting zones, and this will be creating some kind of a foam. We will see some figure maybe for composite propellant, I will show you. In this fizz zone, that NO and NO2 aldehyde whichever are formed in the foam zone, and other CHO and unburnt hydrocarbon species are released and reacted to form NO and hydrogen, carbon monoxide and also the carbonous matter exothermically, such that the temperature will be increased from Ts to the Td. And during this process bubbles and froth are often formed in small thickness, and this thickness will be around something 1 to 10 micron. And this thickness of the fizz zone, which will be basically something will be deciding the burning rate. Let us look at the dark zone. In this zone basically NO, hydrogen, carbon monoxide, carbonous matter will be reacting, and the N2, NO, water and carbon monoxide and carbon dioxide will be formed, and this zone is maybe quite larger as compared to other zone. It will be something 1 to 20 mm, that depends on the reaction which is going on and also depend on the pressure. And of course, a lot of research has been done, but it is not very clear what are the reactions, but some reactions which are important in the dark zones are H will be reacting with water going to the hydrogen and OH, and carbon monoxide will be reacting with OH into carbon dioxide and H radical, and 2NO will be reacting with hydrogen getting it 2HNO, and this 2HNO will be reacting with hydrogen going to water plus N2, and this is a quite a fast reaction. And if you look at this I can say reaction 1, 2, and this is 3 and 4. The reaction 3 is basically third order reactions. So, therefore, overall reaction will be between the second order and third order, and keep in mind that this reaction is a will be giving little bit amount of heat, and then if this is not very much there, then it will be both the exothermic and endothermic reaction will be taking place with little or no change in the temperature, because the heat release is almost negligibly small, and this is a very important zone, particularly when the chamber pressure is less than 7 megapascal. But if it is greater than 7 megapascals, then this will become 0, and the flame zone will be coming very closer to the phase zone. And keep in mind that this zone, if it is extended, then it may lead to the combustion instability. Therefore, it is important to avoid that, and keep in mind that the pressure is this will be occurring at a low pressure. The flame zone is the combustion product, nitrogen and water and then carbon monoxide are formed as a final product with a rise in the temperature. Therefore, there will be rise in temperature and in a very small thickness, which will be around something 100 to 2000 micron. And when pressure is less than 1 megapascal, no flame is formed due to slow reduction of NO to the N2. So, that is whereas the NO, and when NO is reduced to the N2, then is basically giving the very high temperature or the due to the exothermicity of reaction, and that will make the temperature to increase in the flame zone. Thank you very much. In the next lecture, we will be discussing more about the composite propellant combustion. Thank you very much.